Okay, this is podcast 2.7 for chemistry, and we're going to talk about electrons in the atom and electron configurations. So we had Niels Bohr, who had this idea that we have protons and neutrons in the center in the nucleus, and that the electrons exist in shells, or energy levels, around the nucleus. Kind of like planets orbit the sun is what he thought electrons do around the nucleus. Well, that wasn't exactly true. What we have come to find out is that electrons do not exist in these clear-cut defined areas around the nucleus. They exist in what we're going to call orbitals. So they're energy levels that don't have defined areas. It's kind of a fuzzy area where you would expect to find an electron. And that stems from Heisenberg's uncertainty principle. He said that it's impossible to know both the speed and the position of an electron at any given time. We can't know both those things about electrons. What we do then is scientists use math to calculate the probability of finding any electron of an atom in any specific region around the nucleus. So this is the quantum mechanics. And quantum mechanics is based all on calculus. So we're not going to, of course, get into that because we don't want to do calculus-based math. But what they found out is they can predict the probability of finding electrons. So they can predict, if I have my nucleus, that the probability of finding an electron maybe is in this fuzzy area right here. It's not in a nice, neat, defined orbit, but it's more like a fuzzy area is the highest probability for finding electrons around a nucleus. And we can see in different energy levels what those show up and look like. So with that, kind of a visual of what that looks like is these pictures right here. So you can see in the lighter areas where there is a very high probability we would find electrons. And what you should also notice is that these orbitals show up in different shapes. It's not just nice, neat spheres like this. You can get different orbitals with different shapes. So looking on this next slide, this is the different shapes of those orbitals. So within the energy levels, within the first energy level, if we have our nucleus, we'll put the positive charges. Within the first energy level, there are S subshells. Within the next shell, we can have S's and P's. So even within the energy levels that the electrons are in, they also can break down further into what we call subshells. And there are 4 different types of subshells. There's the S, the P, the D, and the F. And the S can hold up to 2 electrons, the P can hold up to 6, and the D can hold up to 10, and the F can hold up to 14. So if we look at these pictures, we can fit 2 electrons within this S orbital, and that's where the 2 come in. This can hold up to 6, so we would have an electron, an electron, an electron, an electron, and an electron, and an electron. So these different orbitals kind of come together to create one big shell where we would see electrons, or where we would predict that we would see these electrons if we could look, at the atomic level of these atoms. And the D's, they get a little kind of crazy looking here with that one, and then the F's even more so. So you just need to understand that within the energy levels, we also have subshells that we can break down the electrons into even farther. So in order for us to describe the location of electrons, we do what are called electron configurations. And there are 3 parts to an electron configuration, and that's what you're seeing right here. The first part is called the shell or principal quantum number, but you can just think of it as the row number. We talked about the row numbers on the periodic table being 1 through 7. So that number is going to be 1 through 7. The next part that we include is the letter. It's S, P, D, or F. So those are the 4 that you're going to plug in here, one of those 4. And then you're going to also include how many electrons are being held in that subshell. This could be 1, it could be 2. It just really depends on which of those letters you use, how high that number can go. So those are the 3 different parts we're going to include in our electron configurations. Now when we're trying to figure out what order these electrons will fill into an atom, We want to know that they go from the lowest energy to the highest energy all the time. And that is always the same order. They always will fill the first energy level's S's first. Then they'll go to the second energy level and its S. And then you'll fill the second energy level and its P's. And you can follow this diagram right here, which is on your handout, and it'll tell you exactly the order that it fills in. One thing you need to pay attention to is that as we go from the second energy level and then we go to the third to the fourth, this starts getting kind of mixed up, because if it's easier to see if you look over here, you have the 3S and then the 3P, but then it fills the 4S. So it goes to the fourth energy level and then it jumps back to the third energy level. So you can get these energy levels that overlap, which accounts for the weird ordering where we're jumping from the third to the fourth and then to the fifth and then back to the fourth. So it's not this really nice, neat, it does the 1S, then the 2S, then the 2P. It's not a really nice, neat order. You really got to pay attention to what's happening. But we can use the periodic table to predict how that will work. So you need to get out that periodic table that's on the white sheet. It looks like this is just not colored in yet. You need to make sure that you kind of make these distinctions between these four different areas. Remember how we said there's the S, the P, the D, and the F? Well, here they are. So I have the S, the P, the D, and the F subshell. And the S's we're going to say are here. The F's here, D's here, and P's here. I'll explain the -1 and the -2 in just a second. All I did down the side was I just numbered rows 1 through 7, just like it is on the periodic table. And this one looks different because we have taken the lanthanide and the actinide series, those two rows that are normally pulled out and at the bottom of the periodic table. I've put them back in where they belong. And I'll show you how this works in just a second. So make sure you color code, write this down. Your periodic table needs to look like this. You also need to know that the S subshell can hold 2 electrons. The P can hold up to 6. The D can hold up to 10. And the F can hold up to 14. Now if you ever forget, S can hold 2, 1, 2. It's 2 columns wide. The P can hold up to 6. 1, 2, 3, 4, 5, 6. It's 6 columns wide. The D can hold up to 10. It's 10 columns wide, and the same with F. It's 14 columns wide. So if you ever forget how many those can hold, you can just count the number of columns and it'll remind you how many can fit in there. So I have found that the easiest way for me to get you introduced to this is just by starting into electron configurations. I am just going to go for it here. We're going to pick some and you can just watch for a while if you want what I do. So let's do helium. If I wanted to write the electron configuration for helium, I start and we're going to read like a book. So read the periodic table like a book. That means we're going to go left to right, top to bottom, and we're going to go row by row. So, like I said, there are 3 parts to your electron configuration. Helium would be 1s2. It would be the second one over. And if you're confused, it's okay, hang on. Lithium. Lithium, I have to start up here. 1s2, because there's 2 electrons. And then there's nothing else in this column. So then I go 2s, and I just smash it all together. 1, because lithium is 1 over. And if you check this out, these superscripts add up to the number of electrons that should be there. They add up to the atomic number. So 2, 2. 2 plus 1 is 3. Okay, let's keep going. Let's do carbon. Start at the top again. 1s, I go through 2. Nothing else in that row. Then I go 2s, and I go through that. 2. And I go over to the 2p's. And to get to carbon, it's 1, 2 over. So 2 plus 2 plus 2 is 6. There's the 6 electrons right there. Let's do one a little farther down. Let's do sulfur. Sulfur is way down here. So I'm going to go 1s, 2. 2s, 2. These are all starting the same. And then I go 2p, and I go all the way across that row. so 2p6, and then I go to the next, so 3s2, and then I keep following this across, and I get to the 3 p's, and I count 1, 2, 3, 4 over. So there's sulfur. Let's pick one of these D's. Let's pick vanadium. All right, the reason that there's D minus 1 is because when I hit this, I need to subtract 1 from the row number. So that means that this is actually the 3 D's and this is really the 4 D's. So even though it's in the 4th row, these are the 3 D's. These are in the 5th row, these are the 4 D's. So with vanadium, I start at the top, 1s, 2. Then I go 2s, 2, 2p6, 3s, 2, 3p6, 4s2, and then I watch out because these are the 3Ds. Oops, I should probably put my 2 in. 3D, 1, 2, 3 over. And there's vanadiums. And yes, I can give you one clear down here and make you do it. But let's just say that one out loud. Let's say I'm going to the americium down there. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f, 5f7. So these can be really, really long. Yes, you have to include all of them when I ask for regular notation. There is a shortcut. Here's the shortcut, and you can only do it when I say so. The shortcut uses the noble gases. Remember, the noble gases are in this family right here. How you do it is, let's say we want to do that americium that's way down here. What you would do is you always want to go up a row all the way to the noble gas that comes before it. So with americium, I go up a row all the way to the end. I'm going to use radon. So I'm going to put americium here. You put the noble gas in square brackets, and that represents all of this electron configuration stuff, all of it through radon. So then I only have to write out the row electron configuration. So I have to start with 7s2, 5f7, because it was 1, 2, 3, 4, 5, 6, 7 over. Let's pick another. Let's go to cobalt. Cobalt. We go up a row to the end. We're going to use argon. So argon, I'm through there. I start in the 4th row that cobalt is in. It would be 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. 3d7. Let's do one more. Let's say I want to do tin. Up a row all the way to the noble gas. So for tin, I'm going to put krypton in square brackets, and then I just do the 5th row. 5s2, 4d10, 5p2. So if you're still not understanding these, it's not a big deal. We're going to do a bunch of practice in class. Okay, there's also something called orbital box diagrams. It goes right along with electron configurations. And if you remember back to this, we know that each of these subshells contains orbitals, and these are the orbitals. The individual pictures you see are the orbitals. So what we do is with the S, since there's only one orbital, the S equals one box. The P's, there are 3 different ones, so the P equals 3 boxes. So S equals 1 box when I draw it. P equals 3 boxes when I draw it. D equals the 5 different boxes because there's 5 different orbitals within these sublevels. So D would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, and F would have 7, all of these down here. These are important. Each box can hold 2 electrons. So if I were to draw electrons, we use arrows. That's an electron spinning up, that's an electron spinning down. So if I were to fill this up, my 2 electrons would look like this. If I were to fill this up, it could have 6 electrons because it has 3 boxes. This can have 10 electrons, and you should be saying to yourself, oh yeah, that's what we just said on the last slide, that the S can hold up to 2, this can hold up to 6, this can hold up to 10. You have half the number of orbitals because each box can hold 2. So the S is 1 box, and the P is 3, and the D is 5. I don't think I ever have you fill in for the F's because that's just too far down the periodic table. So if I want to do these, I gave us a little template to fill in here. It goes along with the energy levels of the different, 1s2, 2s2, because this is the order you fill them in. You go 1s2, then 2s2, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p. So that's just the regular order. You need to make sure you know these rules though. So Hund's rule, he said that the electrons will take their own orbital before sharing. That means if I'm filling in the 3d right here, I'm going to give everybody their own space, and then they're going to pair up. You can think of electrons like siblings. If there are 4 rooms and 4 siblings, everybody's going to take their own room. They're not going to pair up if they don't have to. Electrons are the same way. The Aufbau principle says that each electron occupies the lowest energy orbital they can. So I have this one. They don't suddenly start filling in the 2p with an empty 2s. They must fill in this order. So there's no exceptions to that rule. And then we have the Pauli exclusion principle that says we can only have a maximum of 2 electrons in each box, and they have to be spinning the opposite ways. So I can't put 2 electrons that are both spinning up in the same box. That does not work. You have to have one going up and one going down. That's the only way they can be together. So doing some of these, let's pick some. Let's do boron as our first example. All right, boron. Boron would be 1s2. Well, let's do this. 1s2, 2s2, 2p1. So we also know that boron has 5 electrons. So we go 1, 2, 3, 3, 4, and then 5. And that matches this up here because we have 1s2, 2s2, 2p1. Let's do chlorine. Chlorine should have 17 electrons. So let's do this a different way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, and if I were to look at chlorine's electron configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p5. There we go, because there's 5 in there. So these are just a visual representation of our electron configurations. Okay, 2 more examples. Let's do calcium. Calcium should have 20 electrons. So we go 1s2, 2s2, 2p6, 3s2, 3p6. And calcium has 2 electrons in the 4s. Those are my 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. That's calcium. For my last one, we're going to do an ion. Let's say we do sulfur. Sulfur would have a -2 charge because it has 6 valence electrons and wants to pick up 2 more. Sulfur ion. Regular sulfur has 16 electrons. But if I'm talking about the sulfur ion, we have 18 electrons. So if I wanted to draw that in, 2, 4, 6, 8, 10, 12, 14, 16, 18. That is going to be the sulfur ion's electron configuration. So it's okay to just add and subtract if it's an ion. You just change the number of electrons that you use. So its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. So make sure you're pretty comfortable with these, but if you're not, again, we're going to do a ton of practice with these in class. So you will get your chance. All right, that's it. Make sure you had color-coded your periodic table and you're ready to do some more practice.